Overview of electric vehicle technologies. There are four electric vehicle technologies: motor drive technologies, energy sources technologies, vehicle to grid technologies, and battery charging technology. Here we'll discuss about the energy source technologies. The energy source technology is nothing but it is the storage device which is providing the energy to the motor of the electric vehicle. Considering the properties and feasibility, there are four viable energy sources. One is the electrochemical batteries, simply called as the batteries. Then ultracapacitors, they are called as supercapacitors. Flywheels, they are called as the ultra high speed flywheels, and fuel cells. Here we'll discuss electrochemical batteries and ultracapacitors or supercapacitors. The batteries are the electrochemical devices that store electrical energy during charging and produce electricity during the discharging. So there is always charging and discharging phenomenon connected with the electrochemical batteries. The ultracapacitors are essentially capacitors with ultra high capacitance that store and produce electrical energy by electrostatic means. The ultra high speed flywheels are electric machines rotating at ultra high speeds, very high speeds that store and produce electrical energy by electromechanical waves. They work as motors during charging and serve as generator during the discharging. This is about the flywheel. The fuel cells is the another energy source. These are the electrochemical devices that directly convert chemical fuels into electricity. Considering these four energy sources, that is batteries, flywheels, supercapacitors, and fuel cells, none of them can simultaneously offer high specific energy and high specific power, which is a requirement for the drive energy source so that it can provide long distance discharging for the vehicle. It will provide the required torque also with high specific power, and it should have the storage should have minimum size and weight. So all these requirements are not possible with all these, or none of them will be offer both the properties of high specific energy and high specific power. We'll discuss briefly about the electrochemical batteries. Now, but batteries are the most popular energy sources, and they are still the major source of energy for the electric vehicles. The major type of batteries for electrical vehicles were past few decades. They are include the wall regulated lead acid, VRLA, nickel cadmium batteries, NICD, nickel metal hydride batteries, NIMH, zinc, air, sodium sulfur, that is NAS, and lithium ion batteries. So these are the few among the various or large types of electrochemical batteries. Among them, VRLA is accepted for low cost, low end electrical vehicles. Nickel metal hydride is preferred for well performed electrical vehicles, and lithium ion is attractive for high performance. At present, the status of battery technology, electric vehicle can only offer acceptable driving range with affordable price. In order to enable the electric vehicle offering comparable price and driving range as the IC engine vehicle, the battery specific energy and cycle life need to be increased, whereas the battery initial cost needs to be significantly reduced. So these are the challenges to increase the battery's specific energy, life, and reduce the cost of the battery. The research on battery technology is being focused on the development of various lithium-ion batteries, such as use of lithium, nickel, manganese, cobalt for the positive electrode to improve the specific energy and safety, and the use of lithium titanate for negative electrode to improve the cycle life and charging time. Another key research direction is to develop lithium-air battery and lithium sulfur batteries to significantly improve the specific energy of the battery energy storage. This is the list of major types of batteries that have been developed for electrical vehicle for the past few decades. Also, if you see these batteries, that is VRLA, nickel cadmium, nickel metal hydride, zinc air, sodium sulfur, and lithium ion batteries. They are compared on the basis of specific energy, watt hour, that is watt hour per kg, specific power, watts per kg, life, that is cycles, number of cycles, and cost. This is a relative comparison of these 6 types of batteries. Among that, we can see the lithium ion battery stands the best one, with cost it is lesser, life is significantly good, also specific power is comparatively good, and also the specific energy considering the other factors. The second energy source or energy source technology is the ultracapacitor or supercapacitors, or also it is called as a double layer capacitors. The supercapacitors are based on electrochemical cells that contain 2 conductor electrodes and an electrolyte and porous membrane that permits the ions between the 2 electrodes. Thus, the layout is similar to the electrochemical batteries. The main difference between the supercapacitor and batteries is that no chemical reactions occur in the cells, but the energy is stored in the cell. The supercapacitors, electrode and the electrolyte are electrically charged. Cathode is positively charged and anode is negatively charged, and the electrolyte contains both positive and negative ions. At each of the electrode surfaces, there is an area that interfaces with the electrolyte, and it is in each of these areas where the phenomenon of electrical double layer occurs. If you see the conventional capacitor, which will have 2 parallel plates separated by 2 parallel plates by a dielectric material. When supply is given, charges are induced as shown in the diagram. So this is a conventional capacitor. In the supercapacitor, or called as electric double layer capacitor or ultracapacitor, the construction is slightly modified where the electrolyte layer is added into the conventional capacitor. So the important feature is the electrolyte layer is there in supercapacitor. In this diagram, we can see the detail of a supercapacitor, detailed construction of supercapacitor. By applying the voltage between the electrodes, both the electrode and the electrolyte become polarized. The positive charge of the cathode is transferred to the area interfacing with the electrolyte, forming a layer of positive ions. Also, in turn, the negative ions of the electrolyte are transferred to the same electrolyte or cathode interface, forming a negative charge balancing layer of ions. So these 2 layers build up an electrical double layer The mechanism behind the operating principle of this double layer can be explained with the Helms model. This model establishes that the two layers are separated by a layer of solvent molecules of the electrolyte called the inner Helmholtz plane. So we can see these two layers forms. This is one layer, and here is another layer. So double layers are formed because of this. This layer of solvent molecules actually separates the positive and negative charges of the electrode and electrolyte, thus acting as a dielectric. So there is a potential difference between the two layers of positive and negative ions derived from the electric field within them, and the double layer can be taken to resemble a capacitor. In ultracapacitor, a dielectric is provided by solvent molecules of the electrolyte. In this way, the selection of electrolyte is key for ensuring the maximum energy capacity of the ultracapacitor. Usually, both aqueous and organic electrolytes are found, and the organic electrolyte are the most common type of electrolyte used in supercapacitor. With aqueous electrolytes, a cell voltage of around 1 volt can be obtained, while it can be increased up to 2.5 volt by using organic types. The ultracapacitor technology offers exceptionally high specific power and practically unlimited life cycle. Its specific energy needs to be greatly increased while its initial cost has to be reduced. These are the ultracapacitor technology. In order to maximize the capacitance, different metal oxide electrodes, electronically conducting polymer electrodes, and activated carbon electrodes are used in the industry. These materials are porous, so they can maximize the effective area of the electrode in which ions can be allocated. The most common types are the activated carbon, since they can lead to supercapacitor with high energy density, which is the requirement, and capacitance, very large capacitance. Capacitance up to 1,000 times per unit volume more than those of conventional electrolyte capacitors can be obtained. The electrolyte and electrode material have a fundamental influence on the energy and power capacity of the supercapacitor. So what type of electrolyte used and what type of electrode materials are used will decide the value of the supercapacitor and also its dynamic behavior. The dynamic behavior is related to the charge discharge time constant, that is tau. As it can be seen, the standard formula for the capacitance calculation is C is equal to epsilon A divided by D, where C is greatest in capacitors made from materials with high permittivity, large electrodes area A, and small distance between the plate, that is D. So capacitance is proportional to epsilon, proportional to area, and inversely proportional to the distance between the plates. As a result, double layer capacitors have much higher capacitance values than conventional capacitors, arising from the extremely large surface area of activated carbon electrodes and the extremely thin double layer distance in order of few angstroms. The amount of charge stored per unit voltage in an electrochemical capacitor is primarily a function of electrode size. Present research on ultracapacitor technology is focused on the improvement of its specific energy using graphene and carbon nanotubes to increase the usable surface area and hence the energy storage capacity.